In this lecture, we are going to study about Newton's law of viscosity. In the previous lecture, we have learned about viscosity, what are the causes of viscosity in liquids as well as gases. Then we have studied about different consequences of viscosity and how these consequences will affect the flow behavior of a fluid we have seen in detail. Now today, in this lecture, we'll learn about the very important law which is known as Newton's law of viscosity. So to do that, first we will consider one example. So let us consider between these are the two parallel plates we have, and between these two parallel plates, one fluid element is kept. And on this top plate, a tangential force of F is applied. So two parallel plates between which we have fluid element placed, and on the top plate we are applying a tangential force of F. So when we apply this force F onto the top of it, there will be certain deformation. So this is deformation shown here. So this phi, it is a shear strain because of the shear stress developed at the top of the plate. So now what is the shear stress developed? So it is nothing but force per unit area. So this tangential force, it is being applied onto the area which is perpendicular to the plane. So whatever the plane we see here, perpendicular to this plane, whatever the area we have onto which the tangential force is acting, so that the force per unit area, it will give you shear stress. So because of the shear stress that we have applied, some shear strain have got developed. Now this behavior will be shown by both solids as well as fluids. But in case of solids, what will happen? This will give you certain permanent deformation. So this much amount of permanent deformation we will get by the application of this particular force F. But in case of fluids, what will happen is, for whatever the time duration will apply this force, the fluid element will continuously go on deforming. So it shows that initial deformation was this much, and as continually the force F was applied for the long time duration, the deformation continuously goes on increasing. So it shows that whatever the shear stress that is being developed here, it is proportional to shear strain rate. Now what is the meaning of rate? So in case of solids, we can easily say that shear stress is directly proportional to shear strain. But here, this shear strain in case of fluids, it is continuously changing with respect to time. That's why we need to take into consideration the time element here. And hence, now here we are defining the Newton's law of viscosity as, it is nothing but the shear stress developed, which is directly proportional to the rate of shear strain. So shear strain divided by time, it is nothing but the rate of shear strain it will give you. So the statement of Newton's law of viscosity, it is like this. So it states that shear stress tau, it is directly proportional to rate of shear strain. So shear strain per unit time, it will give you rate of shear strain. So this statement, it is nothing but a Newton's law of viscosity. Now in the next part, we are going to derive this Newton's law of viscosity. So to derive that, let us consider a fluid element A, B, C, D we have here. Now what we are considering is this fluid element, and bottom portion of this fluid element, that is AD, it is in contact with a solid boundary. So as it is in contact with a solid boundary, here we will have a layer which is having velocity equal to that of the solid boundary. So let us consider the solid boundary is stationary. Definitely AD will have velocity equal to 0. So this is nothing but a no slip condition that we are considering here. Now let us consider on the top of this element, that is on this BC part, and perpendicular to the plane that we are considering, it is having a thickness of S. So the area we have is BC multiplied by thickness of this element. So BC into S, it will give you the area. So onto this area, let us now consider that we are applying a shear force of F. So on BC multiplied by S, on the whole area, we are applying a shear force of F. So definitely it will develop certain shear stress tau, which is F upon A. Now because of this force which is applied onto the area A, what will happen? The element will get deformed. So the element which is ABCD, it is getting deformed to AB dash C dash D. Now this molecules are not moving because here we are considering the no slip condition. Now next to this, Now we can identify the shear strain we have. So this deformation we are considering only for certain time duration t. So let us consider in time duration small t, after application of the shear force F, the element has got deformed from A, B, C, D to A, B dash, C dash, D by a shear strain value of phi. And now let us consider that on this CD element, on this side CD, we are considering one particle which is particle E, and in time duration small t, this particle has traversed some distance. So it has moved from this point to this new location. So now let us consider that suppose that in time t, a particle E moves through a distance x. So whatever the distance it moves, it is distance x. And now if it is at a distance of y from AD, so from AD it is having certain distance. So these distances we will define now. So what we have done till now? So ABCD was the element. On the top of this element, which is having area A shear force was applied. So ABCD has got deformed into A, B dash, C dash, D, and it has given a shear strain of phi. And all these things, it is happening in the small time duration t. Okay. Then we have considered one particle at location E. On this side is CD. So this particle in time t, it has moved certain distance. Now what is that distance? It is the distance x, which is moved by particle at this location in time duration t. And this particle, it is at a distance of y from this plane AD. Now will we know what is the shear strain? So shear strain is nothing but what? This much is the shear strain. Now here again the angle will be same, phi. And now here we are having a right angled triangle. So here we can make use of trigonometry to calculate this phi. So tan phi, it will be equal to opposite side upon adjacent. So this is the opposite side and this is the adjacent side. So opposite side is x and adjacent side is y. So as this deformation is very small, because we are considering a very small time duration, so tan phi can be considered equal to phi, and we can write the shear strain equation as phi equals to x upon y directly. Now here, as we understood that in case of fluids, there is no permanent deformation we have. We have continuous deformation. That is the deformation phi, it will change continuously with respect to time. So here what we will find is, in this time duration t, whatever the shear strain that is occurred, and we write this term as rate of shear strain. Now what is rate of shear strain? It is phi upon t. So shear strain per unit time. So shear strain in time duration small t. It is nothing but rate of shear strain. Now this phi we have calculated as x upon y. So putting here phi equals to x upon y. So x upon y divided by small t, it is equal to, now we are shifting this y in the denominator, so it will be x upon y into t. It is equal to, now separating the terms, so that we are separating it as x upon t multiplied by 1 upon y. So x is the distance covered by this particle at location E, and t is the time taken to cover this distance of x. So distance upon time, it will give you velocity. So x upon t, it is velocity u of the particle which is at location E, and divided by y. Y is nothing but what? It's a distance from this plane AD. Now assuming experimental results that shear stress is directly proportional to rate of shear stress. So in the previous example also we have understood that in case of fluids there is a continuous deformation. So definitely shear stress will be dependent on the time element. So shear stress will be directly proportional to rate of shear stress. So same experimental result we are assuming here, and according to this experimental result that shear stress is directly proportional to the rate of shear strain, what we can write here it as tau is directly proportional to rate of shear strain. What is the rate of shear strain equation? U divided by y. Now if we replace this, if we remove this proportionality sign, the proportionality constant will be involved here. So tau equals to constant multiplied by u by y. So this constant is a proportionality constant, and it's denoted by mu. So mu is nothing but what? It is nothing but viscosity. So tau equals to mu into u by y. Now we understand that because of the no slip condition, and when the fluid flows over a surface, the velocity distribution we have, which is parabolic in nature. So velocity is continuously varying from the solid boundary in the y direction. So what we can say is, if different points on this CD we take, so as y is going on changing, the velocity u, it will also change. So we can write this u by y in terms of differential, which is nothing but change in velocity with respect to change in y. So as y is going to change, velocity will change. So this can be expressed in terms of differential terms, which is nothing but mu into du by dy. So tau equals to mu into du by dy. It is known as Newton's law of viscosity. Now as we understood what viscosity is, which is denoted by mu, now we will understand what is the meaning of kinematic viscosity, because while solving different fluid analysis problems, you will come to know that you are making use of the term kinematic viscosity. That's why we need to understand what is kinematic viscosity. So we understood mu, which is dynamic viscosity or viscosity. It is known by two terms, viscosity or dynamic viscosity. And in addition to this, now we are going to learn about kinematic viscosity, which is denoted by a symbol, and this symbol is nu. So this is mu and this one is nu. So this nu is kinematic viscosity and mu is dynamic viscosity or simply viscosity. Now how this kinematic viscosity is defined? It is defined as nu equals to mu divided by rho. Now what is the meaning of mu divided by rho? We will see right now. But one important thing is, though we know about viscosity, we have equations for viscosity. Why there is a need to define kinematic viscosity? Because in most of the fluid problems, in most of the fluid system problems, you will come to know that the two parameters mu and rho, they are always coming in combination. So this kind of combination you will observe, and because of which, instead of using two different parameters, we are making use of a single parameter, which is mu. So a combination of two parameters resulting in a single parameter, and we are directly making use of this parameter in the analysis, and this is the reason why we are defining kinematic viscosity. But apart from this kinematic viscosity, it is also having some physical significance. Now what is the physical significance this kinematic viscosity has? Before that, we'll understand what is the unit for mu. So if you put here the unit of dynamic viscosity and density, you will come to know that the unit of kinematic viscosity is meter square per second. And now we'll understand what exactly the significance of this kinematic viscosity is. So mu is nothing but viscosity, and we understood that mu is a parameter which tries to diffuse the disturbance in the momentum. So what exactly mu does? It causes the disturbance in the momentum of the fluid flow, and hence we can say that mu tries to diffuse the disturbance in the momentum. So this is the meaning of this mu. And what rho tries to do? So rho tries to maintain the momentum, because rho is associated with mass term, mass per unit volume. So mass, again, it is associated with inertia and momentum, and hence we can say this rho, it will try to maintain the momentum. Now what exactly this mu, which is a combination of this mu and rho? So it is an indicator of relative tendency of diffusing the disturbance in the momentum as compared to the tendency to maintain the momentum. So mu is going to disturb and rho is going to maintain. So from this we can understand the physical significance of kinematic viscosity.